Good afternoon, TechNation. Welcome to Webinar Wednesday. We are excited to have nearly 700 registered attendees for today's webinar, which is eligible for 0.1 CE credits from the ACI. We're going to kick off today's call by giving away a TechNation t-shirt to one lucky attendee. If you can answer the following question using the questions feature on your dashboard, do so now. The question is, which famous U.S. Olympic women's soccer team player originates from Washington State? The question again, which famous U.S. Olympic women's soccer team player originates from Washington State? While you are answering, I want to invite everyone to join us for the MD Expo, which will bring together HTM professionals from across the nation to New England for 3 days of learning, networking, and the latest advances in technology, products, and services. Registration is now open. You can receive complimentary admission by using the VIP Pass compliments of Fluke Biomedical, which you can find in your Webinar Wednesday workbook. All right, everyone. The winner of our TechNation Tour t-shirt is Jim Scott. Congratulations, Jim. And for the rest of you, the correct answer was Hope Solo. TechNation would like to thank our sponsor, Fluke Biomedical. They are the premier global provider of test and measurement equipment and services to the healthcare industry. They serve biomedical engineers, quality assurance technicians, medical physicists, oncologists, radiation safety professionals, and are continually expanding their range of solutions to a broader range of health and safety professionals. Learn more at flukebiomedical.com. Our presenter today is Jerry Zion, Global Training Manager for Fluke Biomedical. Jerry, you may begin whenever you are ready.
Great, thanks so much. Welcome to Advantage Training and the Wednesday webinars. The topic for this session is everything you wanted to know about electrical safety testing but were afraid to ask. And we hope to clear up confusion about some testing situations that we know confront you daily, but that few people are talking about or teaching about. So let's get started. We'll cover the questions you're asking us most about, which include medical devices that are permanently connected to mains, whether those be regular power, single-phase power, or three-phase power, and including isolated power distribution considerations. We'll cover Class 2 medical devices and Class IP medical devices and what the standards say about how those ought to be tested and some things that you'll run into. We'll answer the question which electrical safety standard to use and when to use it relative to the IEC or international standards 60601-1, 62353, and the IEC61010, whether to use that or 62353. In terms of the 62353 standard, we're going to help you learn how you can choose and when to use the 3 different methods of testing that are applicable in that standard: direct, differential, and alternative. So among the challenging situations to understand how to perform appropriate electrical safety testing are when the electromedical device, the EM device, is permanently connected to mains power or an isolated power system or a three-phase power system. We'll also try to clear up some other things, for example, those centrifuges that are floor models that may or may not be permanently connected to mains, treadmills, cardiac stress test systems, diagnostic X-ray for rad fluoro, and some other considerations, for example, CT and some other modalities. Let's start off by answering the question, which standard should I be using? The IEC 60601-1 is really intended for design type testing for medical device manufacturers. That's who it's written for and who should be using it. There are two particular key areas in a manufacturer like that in which they should be using the 60601-1. In their design validation testing, which is controlled usually by R&D quality or someone from the quality department, and also in operations or production or even refurbishment in their final assembly testing. And the reason for that is it's the first time that the particular serial numbered medical device has been completely assembled, and so it needs to be tested just as if it was a design prototype. The IEC62353 is an end user customer focused standard. Also should be used for field service engineers, whether they're part of a medical device manufacturers organization or a third-party service provider. So the areas that can be that the 62353 can be used in include acceptance or incoming inspection testing at the hospital or medical facility, periodic maintenance and testing, that's our routine every month, twice a year testing, whatever we're doing. Post-repair testing, when the electrical safety tests are done after the medical device has been delivered to and installed in the end user customer facility, even if they're in the clinical laboratory or the research laboratory. Still, 62353 is the appropriate standard to use. The IEC61010 is used during design and design validation at the medical device manufacturer factory, but it's not intended for routine use, even though it's called out for clinical laboratory equipment. In fact, it has no information about what the testing methodology is supposed to be or how the medical device shall be connected in order for that testing to be done. It only has the allowable leakage current in it, and so the advice from the standards committees is to use IEC62353 just like any other medical device in the hospital or medical facility. So there's one consideration. If the power supply voltage provided to the medical device is less than the nominal voltage coming from mains, so if you're in the United States, less than 120 volts AC, or if you're in any other part of the world, less than 230 volts AC, then the value that's measured should be multiplied by the result of 230, or the nominal voltage, divided by the actual measured voltage of the main supply. That correctly compares with the limits indicated in 62353 in the standard, so that's what you would use. So there's a little bit of a calculation to do there, and you have that in your workbook, that formula that you need to use. So other variables in testing under 62353 include the type of the mains supply system, the electromedical device installation, how it's installed, and the measurement method that applies. And there are two decision trees that we'll go through in a minute to help you figure out which you use and when is the right time to go through that decision tree. For medical devices that are permanently connected to mains power, leakage currents under IEC62353 is required only if the accessible voltages are over the limit. Otherwise, there is no requirement for electrical leakage testing. For medical devices operating on three-phase mains power, IEC says that we are authorized to test, that we're authorized to do that testing and especially for medical lab equipment using 62353. The type of the main supply system. This can be a little bit confusing, and we were looking for but did not find the express description of a TN-S versus a TT. for example. So we'll continue to look for those explanations for the terminologies, but basically there are 5 different main supply system types. And these are TN-S with 4 active distributed conductors and voltage 400 divided by 230 volts, which is generally present in all large public and private healthcare facilities. The type TT, also with 4 active distributed conductors and voltages of 400 divided by 230 volts, which is generally present in smaller public and private healthcare facilities that require less than approximately 100 kilowatts for power. The type IT-M, 230 volts, the type TN-S, and the type TT, these all have 3 active distributed conductors and phase voltage of 230 volts or around 220 volts. So these are the types of main supply system that you will find. So identifying which one of these is important so that you report the voltages and calculate the necessary adjustments properly under 62353. The type of electromedical device installation is also important and relevant. So we can have movable single-phase or 3-phase equipment with the possibility of being completely isolated from the ground during the measurement, with connection to the mains power supply through a plug or a plug-in socket connection. So these are the kind of movable devices, whether single-phase or 3-phase, that plug into a mains outlet in the wall. We can have movable single-phase or 3-phase equipment with permanent connection without a plug or a socket connection to the power supply. We can have fixed single-phase or 3-phase equipment which cannot be completely isolated from the ground during the measurement with connection to the power supply through a plug and socket connection. Or we can have a fixed single-phase or 3-phase equipment with permanent connection without a plug or socket connection to the power supply. Internal electrical power source equipment is also a possibility. These are typically those devices that are operated on battery, whether or not that battery is rechargeable. So these are the types of electromedical installations that occur to those types of main supply that we listed. These are all things to take into consideration. Now we move to under IEC62353, which is appropriate for us to use in testing on a repeated testing basis, whether that repetition is every once per year, twice per year, or the like in a medical device facility, no matter what the medical device is, whether it's permanently connected to mains or whether it is removable and able to be connected through the electrical safety analyzer. So this is a decision tree for a class 1. So let me just be real clear here. We're talking about a class of medical device that comes from the electrical safety standard about electrical safety and electrical power. It has nothing to do with the FDA, United States FDA device classification, which is about patient risk. So this is class 1, class 2, or class IP for electrical safety. Do not confuse it. The medical device will have an indicator, a stamp or a mark on it someplace that will say the FDA classification, but that has nothing to do and is inappropriate for you to use when you're thinking about electrical safety. Be sure you understand the electrical safety classification. A class 1 medical device for electrical safety purposes is one that connects to mains power through a plug typically, or a mains connection that includes a ground and that has an accessible ground or permanent earth test point on the device. That's class 1. And that's what we're going to follow through the decision tree to see which of the 3 testing methods under 62353 that we would follow. So we have the measurement of the leakage current for class 1, and the question, is the protective earth resistance okay? Does it pass the requirements of the standards test? The answer is yes or no. If the answer is yes, then we move to the next question to the left, which says, does the equipment contain any active circuitry? And the answer will be either yes or no. If the answer is yes, we move to the right, and we have to answer the question, is the medical equipment have an active switch in it? And that active switch result, yes or no, is what determines whether we can use the direct or the differential measurement methodology. No matter what the methodology is, if we have applied parts, that is ECG lead wires or anything that connects directly to the patient that has a continuous conductive connection to that patient, like an ECG lead wire does through the ECG electrode, that means that we are required, I repeat, required to do the applied parts testing, in particular mains on applied part. So the mains on applied part tests are voltages that on Fluke Biomedical test, electrical safety analyzers anyway, is outputted through the applied part lead post at the top of the device. So that's where the mains voltage is going to come out for mains on applied part testing. Under IEC62353, that's going to be just regular mains. There's no up transformation of that voltage. So if we have no automatic switch, then we're able to use the alternative method. So back all the way to the left where the decision says no active components and no switch. So then we're still required to do the applied part testing for any applied part that is BF or CF. F meaning float. So an F type is a BF or a CF connection to the patient, and then you're required to do the mains on applied part test. But you can do the alternative method if there's no active switch. That's the real deal in terms of the decision tree. You make this decision on incoming inspection of the medical device. As it comes into your facility, if it's not already called out in the manufacturer's service manual inspection procedure, you as a medical facility are able to make that decision about which of these 3 test methods that you will use, but you lock it down for that medical device right then and there in the acceptance testing. And then you use the correct workflow or form to fill out or whatever it is that guides you through that electrical safety test. The alternative and the differential method of testing dramatically abbreviate the number of tests that have to be done and determine whether we have to use both power on and power off. In fact, they also determine whether or not we need to use reverse polarity or not. Before I go to class 2 medical devices, let's just have a word about polarity, reverse polarity, while we're talking about it. There are medical devices that include actual computers that really need to power all the way up or power all the way down through their normal power up or power down cycle. Those include, for example, diagnostic ultrasound equipment. That's not the only one that you will run into that is that way. There are others. So in those cases, doing reverse polarity testing may damage the computer, so you don't want to do that. But the real advice does not come from a company like Fluke Biomedical. It really must come from the medical device manufacturer of that brand and model of medical device. In fact, the category of medical device. So let's be real clear, to answer the question of whether or not to do reverse polarity, you really want advice from the medical device manufacturer. If you cannot get that advice and you feel it necessary to make the decision yourself, make sure you clearly state in a deviation from whatever your standard work is in your policy about inspection procedures, that you write a clear statement about that brand and model of medical device about why you will not do reverse polarity testing. Make sure it's clearly documented and what you will do instead. That will keep you, at least in quality assurance best practice terms, in pretty good shape. Now, the next question is what will happen on audit trail when your auditor comes through, and you may be audited as a hospital or medical facility, even by the FDA, but certainly you'll be audited by the state health department. You will be audited by Joint Commission or whoever your voluntary accreditation auditor may be. In the United States, there's a couple of different organizations. One of them is certainly the Joint Commission, but there's another one too. So whichever one is that, it will be up to the auditor what they're going to hold you to. But technically, they should hold you to what you say you're going to do in your policy. All right, let's go to Class 2. If you read through this decision tree, you're going to see that it's very much the same as the other. The difference will be for a Class IP device, which is one that has a battery or an internal power supply of some other kind. The Class 2 medical device for electrical safety purposes is one that may not have an accessible protective earth or ground test point. It is typically one that is completely plastic on the outside and non-conductive. So even a touch current or chassis leakage or enclosure leakage test point may not be available. So in this classification, double insulated is really the way we should be thinking of this. Class 2, double insulated, may or may not have an accessible protective earth, probably will not have a touch current test point, which is a non-earth conductive test point available to us. In those cases, and in the cases of a Class IP device, which has an internal power supply, typically a battery, we need to use a sheet of aluminum foil, not like you wrap your sandwich in. It has to be more thick than that. But we use aluminum foil. We put it in close, good physical contact with the touchable external surfaces of the medical device and tape it down. Just use any tape, tape it down so that it's firm and it's going to stay in place. And then use your alligator clip with your test lead and clip that test lead on there. And you're going to make a leakage current measurement. The leakage current measurement is capacitively coupled from current flowing inside the medical device through the insulator of the plastic of the exterior of the medical device to the aluminum foil, which is a conductor. So the conductor, insulator conductor, is that by definition a capacitor. You will be measuring a capacitively coupled leakage current. It probably will be lower than the leakage current that you would have measured otherwise for this enclosure or chassis leakage current measurement or touch current measurement because of some of the losses on capacitive coupling. But that's what you're going to measure, and you need to document it, and you need to do that testing. So if you're not doing that testing today, you need to start. But it's just a thicker aluminum foil material. In the United States, about a 10 by 10 square of aluminum foil. In other countries, it's a 4 centimeter by 4 centimeter square. We followed the same decision tree, same decisions about are the voltages okay? Did we get the protective earth okay? Is there an active switch, yes or no? And those guide us through whether we can use direct or differential, or whether we can use alternative as the testing methodology for leakage current measurements. Like the other workflow for Class 1, if we have BF or CF applied part types, we still have to do the applied part and mains on applied part test. Okay, we still have to do that. Whether or not we can plug the medical device into the electrical safety analyzer, because remember, certainly for Fluke Biomedical safety analyzers, the voltage for mains power is coming out the applied part connections at the top of the electrical safety analyzer. So that's how we will do those tests in the mains on applied part test and how come it will work. All right. Okay. The IEC 62353 has the following to say, just to give us a little bit more information. Measuring of equipment leakage current shall be performed to give the same result as measured in a single fault condition. So single fault tests mean lifting, opening the ground or opening the neutral wire to see where does the electrical leakage current go and how much is there flowing and where is it flowing. For permanently installed medical equipment, the measurement of equipment leakage current is not necessary if the protective measures against electrical shock in the supply mains are in accordance with a different IEC standard, IEC 62364-7-710. So I haven't looked at that one, but that is the basis upon which we are able to avoid the leakage current measurements. It's if we're following that standard for the connection for the mains power supply, the mains distribution system, we're good to go. Equipment shall be measured in all intended function conditions, switch positions, and that influence the leakage current. The highest value, and so we're doing worst case conditions. The highest value and the related condition, if relevant, shall be documented. So that's what we want. We're going to document the worst case leakage current that we measure. And the measurements according to IEC 60601-1 may be performed if the protection of the personnel and of the environment is guaranteed for allowable values. So you have a choice, but typically we would choose the 62353. It's abbreviated, it helps us get our work done, yet it helps us document electrical leakage on a regular basis, which is important to minimize the electrical risk to the patient who is vulnerable, who has indwelling catheters that may even go directly into the heart. It only takes a little bit of voltage and current flow there in order to do a lot of damage and even cause death. So that's why we want to keep doing it. Okay. What about mains on applied parts? We've already talked a little bit about that. The IEC standard states the requirements for the measurement of this by function. So even if the device is permanently installed and has floating applied parts, such as the detection of electrodes for ECG waveforms in an angiography room, so a cath lab or interventional cardiology room, the mains on applied part test must always be performed with, but you can do it without powering up the patient monitoring section of that system under test via the electrical safety analyzer. So it applies to all of that. Here is an example of some measurements that were made for equipment leakage currents performed on an operating table, and this was a Fluke Biomedical ESA615 electrical safety analyzer was used, powered by each of the three types of main supplies, and those are identified in the tables. So this is two tables. The next slide shows the third table. The first table is for a grounded, ground and neutral system, The second is measurements from an IT type system. And the third is measurements from the ground system. So you can see the leakage currents values for protective earth resistance, for the mains voltage, to make sure that we understand what the nominal voltages are and on which conductive wires of the power cord that we will find those voltages, and how many measurements that need to be made. As you see, remember, this type of supply, main supply, has 4 conductive wires, not just 3. So the open ground condition, single fault condition, returned 23.1 microamps against a test limit of 500 microamps that would have, and therefore resulted in a pass. The open ground reverse polarity returned a little less, 22 microamps. So those were a pass. The tests, so those were the direct method. The direct method under 62353 is the most comparable to the IEC 60601-1. So if you're a manufacturer and you want to match up the measurements that are made in design validation and final assembly test, when your field service engineers are doing their testing, the 62353 direct method is a good one to use as long as there is no active switch in the power supply. So in the case of the alternative method, we had a open ground leakage current of 48.5 microamperes AC against a standard maximum of 1,000. So again, we had a great pass there. And in the differential method, we had back to something similar to the direct method of about 22 and 21, 22 in normal polarity and 21 in reverse polarity. These are just some examples so that you can kind of get in your mind what kind of measurements you should expect to see when everything is working well, no matter which of the types of power supplies you have. I can tell you that from my experience, this is a lot more detail and decisions than I ever felt like I had to make. And I know that it's confusing and that it's difficult to figure that out. You can get some advice from the electricians in your facility or those that are contracted with the hospital if you need to about the type of power supply, mains power supply and distribution system, the way that they have it wired. I would look to them for that advice and make sure we have a clear understanding of how the medical device then is installed and how it's using that main supply so that we can identify the proper way of doing the tests for electrical safety. So in summary, permanently installed medical equipment, medical electrical equipment, the measurement of equipment leakage current is not necessary as long as we're compliant with the IEC 62354-7-710 and the tests are done regularly. So you only have to do the touch current is the same as chassis leakage or enclosure leakage. You only have to do the touch current if there's not a grounded metal exposed part. The isolated power locations, the isolated power is a guarantee for operability and for safety to the patient. Typically, they may include an equipotentially grounded system in the room. So the advice that we've seen when we looked across the industry and the advice that was being provided was that if we can remove the medical device from the room or otherwise plug it into a grounded, earthed or grounded mains power receptacle, that we should do that and make the measurement in that way. The reason is because the isolation transformer doesn't convert all of the electrical current flow to the reference point of the secondary of the isolation transformer. And some of that electrical current remains seeking the ground as its reference and will flow to the protective earth ground no matter what. So if we just make that measurement on the secondary side of the isolation transformer, we don't see the whole picture. And seeing the whole picture is important relative to electrical safety in accordance with the standards and in accordance with our objective of reducing risk to the patient when they're connected to an electrically powered medical device. I hope that helps. There's some more summary here. The equipotential grounded systems, it's mandatory that we make sure that microshock risk is reduced to a minimum. So there is an isolated power system there. Usually, also equipotential grounding will be in use in that case. The same advice applies. Connect the power for the medical device for anything that's movable to a protective earth mains power receptacle, or else bring a power cord, an extension cord in from just outside that room that's connected to a regular main supply, or those are the two alternatives. Either move it out of the room or move it, or have a longer extension cord into the room for that purpose and that purpose only. That advice comes from the standards, so your auditor shouldn't argue with that detail, either from Joint Commission or anyone else. That's the advice that we're getting. For those of you that are still uncertain around the 61010 standard for clinical laboratory devices, remember that 61010 is a type approval, design type approval standard for laboratory equipment medical device manufacturers. The leakage current tests in the standard are required only if accessible voltages are over the limit, and there is no requirement for earth leakage. So we're authorized to test lab equipment using IEC62353. Want to make that clear because there's a lot of confusion out there about this. 62353 is our standard even when we're testing clinical laboratory equipment. There is an application note that we have available for 62353 for looking deeply into the details around the type of main supply, the electromedical device installation, and it does not include the decision tree from this PowerPoint, but you have it now at least in your workbook from us, and that comes directly out of the standard. So we have to be careful, it's copyright protected. You may need to look to the standard and get a larger copy of that from the IEC62353 standard itself. But you can follow the hyperlink here to that application note. If you go to the ESA615 product page, there's also a link to this application note from there as well. That's the information that we have available for you today. We hope it helped. I know it can be very confusing for electrical safety. It's one of the more complicated things that we have to do, even though it seems like it should be so simple. Do have a look at it. Try and become a little bit more deeply educated on the requirements and how we figure all of this out. And you can pose more questions to us at any time. We're always happy to receive them. And we'll open it up for questions.
Okay, Jerry, thanks very much. The first question is, what is the importance of reading leakages in AC only, DC only, and true RMS?
AC only, DC only, or true RMS. So typically the question more comes out AC only, DC only, or AC plus DC, which may be the same thing as true RMS. The measurements are all made in, are all a type of RMS measurement. DC is a little bit different, but we typically make measurements in AC plus DC because it presents the absolute worst case and typically provides higher leakage currents than just DC or just AC. And so since we're looking to document the worst case leakage current is really what we need to document, that works really the best for everything. So our recommendation is AC plus DC.
Okay, what's the best way to test IP devices for electrical safety?
Okay, so we talked about this a little bit already about specifically what the standard says. The best way is to, for mostly the Class IP devices, really, first of all, they don't have a ground. You won't find one in the device as it's powered by the battery only. Now, this does not include the charging stand that it may be sitting upon where it gets an inductive recharge of the battery inside of it. Does not include that charging stand. So we're talking about the IP medical device all by itself with its battery only. And in that case, as I said, there is no ground, so we cannot do a protective earth resistance measurement. We cannot do a leakage current to ground measurement. That leaves the touch current, also called enclosure leakage or chassis current. And that test may be difficult to do because that kind of medical device may, again, be totally encased in plastic, and it may not provide us any conductive surface that is connected to any of the electricity or the current flow, and so we won't be able to get a measurement. That's why the standard says in those cases, you use the square of aluminum foil, put it in close physical contact with the surfaces of the device that the patient could touch while they're connected to it, and tape that down and then make your measurement to that aluminum foil. It will be a capacitively coupled electrical leakage current measurement. It will be the right measurement to document to make sure that your even Class IP medical device is properly or functioning within the testing limits of the standard for electrical safety and is safe and effective for clinical use.
Okay, with only one lead attached in dual lead or patient auxiliary, a current is detected, for example, 40 UA, why?
So it depends on where what that applied part is otherwise connected to. So for example, there are single lead applied parts. And remember, there are three applied part types. There's the B, which is grounded, the BF, which is isolated, and the CF, which is even more isolated from ground. So depending on which kind of applied part it is, will tell us more. So no matter what though, if we have a higher than the maximum test limit, the maximum allowable leakage current, then we need to do something about that. Either replace the applied part conductor, the applied part itself, or if there's a deeper problem in the medical device, we need to troubleshoot that and correct it. So if we can replace the applied part itself quickly, we'll do that, retest, and then move on. If the medical device tests out okay, we'll put it back into clinical use. Otherwise, it goes in the repair queue. So it really doesn't quite give me enough information to really specifically answer that question. Aside from if it's like a temperature probe, that's a single applied part that comes in. There may be a couple of other examples of single applied parts. Typically, if we have a situation like on the Fluke Biomedical IEC612 and IEC615 electrical safety analyzers, we have only 5 lead posts at the top of the device. So if we have a 12 lead patient cable, that's 10 lead wires, then we need to somehow shorten up how long it takes us to do the test. The standard wants us to document the worst case testing scenario. So we could short the 10 lead cable altogether and come off of that with just a single applied part lead. So we combined and connected all of the 10 ECG cables, for example, together. We're coming off with one lead wire. That will have the sum of all the leakage currents coming down each applied part. If we're testing for worst case, if the worst case leakage current measurement exceeds the testing limit, then we failed the test is over, now it's time to troubleshoot. So it becomes a troubleshooting or corrective action at that point. It's no longer about electrical safety testing, it's about troubleshooting and finding the culprit, that is the 1 or 2 lead wires that are producing the over limit. And so we'll troubleshoot and find those, in that case, by connecting 5 lead applied parts at a time to across the top of the safety analyzer, finding the worst case ones and doing, as I said before, replacing the faulty ones. If that solves the problem, we're done. Or and then we can repeat the test, or the overall test, so we show a pass. Or if we need to troubleshoot more deeply, the medical device simply gets put aside, goes in the repair queue, and cannot be put back into clinical use until we've corrected the problem where there's a deeper problem.
Okay, thank you. Can I measure leakage or power cord resistance on a piece of equipment that has a power cord with only 2 conductors, hot and neutral, when it is plugged into the test receptacle?
Nope, the answer is no, you cannot. You have no protective earth to make the measurement on, and that is an example of probably a double-insulated medical device. Otherwise, the medical device is like really old and really ought to be replaced.
Okay, how do I remove the reverse polarity test, power off test, or open neutral test for all of my safety tests?
Oh, that's a very specific question that is test instrument by test instrument specific. So I don't have enough information, whether it's even a Fluke Biomedical electrical safety analyzer, so I can't really answer the question without more specificity. But let me just put it this way. If the tests are going to be avoided by policy and procedurally you're going to change your procedure to show what tests you are not going to do, then you have to state that in policy. You have to make a statement about that and then do what you say you're going to do. Otherwise, if those tests are not included because you have chosen a different testing methodology under 62353, for example, then your form and your fill in the blank, so your form for reporting and documenting should match the procedure from the standard that you say you're going to use, in which case you wouldn't run into the requirement. But if the question is how do I operate my electrical safety analyzer, that is make and model by make and model. And I really can't answer the information with the information that's been provided.
I don't need to test applied parts. What features would I need in an analyzer?
Okay, so this is a good question. You don't have to do, so this tells me you have no applied parts or no continuously conductive applied parts that touch the patient. So this might be an infusion pump. It could be a pulse oximeter. And why that? Because at the sensor that goes on the patient digit or on the patient's forehead or wraps around the baby's foot, those now you are optically sensing the O2 saturation through the tissue, and you are isolated by definition from from the patient for electrical safety. The conductive wires go only to the photo emitter of the sensor and no further. So there isn't anything that's conductive that actually touches the patient. So it could be an oximeter sensor. So if we have absolutely no electrically conductive applied parts that need to be tested, for that device, we could use a more simple electrical safety analyzer. For example, Fluke Biomedical has released in the last few months, last year, the IEC609, which is not capable of applied part testing. You could use that test device, okay, for doing the tests on this kind of a medical device, because you're only going to need to measure protective earth resistance. You need to measure leakage to ground. You need to measure the touch current, also known as chassis current or enclosure leakage, and you're going to need to do that with power on and power off in reverse polarity and normal polarity. You can do all of that with the IEC609. But let me just put another thought in your mind. How many medical devices are in your medical device inventory or that of your client, hospital or medical facility that you're going to go do electrical safety testing on? If you only have a few that are no applied parts, then but you have others that do have applied part testing, are you going to really carry 2 electrical safety analyzers with you to go do that test? I don't think so. So in that case, you have to choose the electrical safety analyzer that fits your highest need, and you're going to use that one whether you have applied parts to test or whether you do not. If you don't have anything connected to your applied part post, it's not going to do the applied part test. You won't be doing those tests. And there are ways that you can use the safety analyzer in order to do that. That certainly applies to Fluke Biomedical electrical safety analyzers. And then I leave it to you to take a look at the one you're going to use and answer the question yourself according to what we've just been through.
Okay. What are the testing requirements for CPAP machines in a hospital setting?
So we've already gone over that. They are typical of the kind of medical device that would be permanently connected to mains power. They are also typical of the kind of medical device that would need 3-phase power coming into them. And so you will follow the what we went through for permanently connected to mains devices. So if the mains power is properly compliant with that other IEC standard, bear with me here, I'm just going to make sure that I give you the right reference. The IEC 63, bear with me for a minute. The IEC 60364-7-710, if we're compliant with that standard in the way that those mains power distribution is installed, then we are not required to do leakage current tests on those permanently connected devices at all. At all. The only test that we would be obliged to do would be the mains on applied part tests if we have and whenever we have any F-type, that would be BF or CF applied parts. So that's the clear answer from the standards committees.
Okay. What type of equipment should not be tested using reverse polarity?
Okay, so I gave an example of the type of a medical device that includes a complete computer, just like you would use anywhere else, in the design of the system that kind of integrates that computer into it. But in fact, what you need to do is take that on a brand and model by brand and model basis, seek advice from the manufacturer of that device as to the appropriateness of doing reverse polarity testing. I worked with one manufacturer in their field service organization recently to advise them about electrical safety, and their decision in their field service organization was that their diagnostic ultrasound systems did not do well with reverse polarity, and therefore they wrote into their policy and procedure that they would not be doing reverse polarity measurements because they did not want to damage the medical device or shorten its useful life. But that has to be done in a policy statement, and you have to say what you are going to do and what you are going to document. Otherwise, on audit trail, you're going to get a discrepancy finding, and which could result in a fine or other actions. So seek advice from the medical device manufacturer of those devices that you are questioning about. So it could be diagnostic ultrasound, for example, or anything else that integrates a complete computer system into it that doesn't have any particular protection, other protection for that computer.
How often should we test Class 2 device in a year?
So that's a good question. So recently, in the last 2 years, the NFPA in the Life Safety Code has changed its advice about how often to do electrical safety. Prior to that, we were saying once per year for all electromedical apparatus, all medical devices. However, the NFPA felt that you could avoid doing it quite that often, and you could put the frequency to where you wanted it to be. However, the CMS, which is the part of the government in the United States that reimburses the cost of care for Medicare and Medicaid patients, and that's not just our old folks, that's also our injured and disabled folks that are coming back from war zones and things like that. What they said was, you will test in accordance with what the manufacturer of the medical device says for frequency of electrical safety inspection, or at least once per year, or you may lose your reimbursement for cost of care of those patients. That is the final word on that in the United States. There isn't any better answer that I can give you. It isn't specifically from the minimum performance and safety standards, but it is an overriding decision that we all have to face. And that's not just hospitals, it's any medical facility.
Okay, thank you. Are all ultrasound systems to be tested under the same standard, and if so, which one? How would you test an ultrasound?
Okay, so let's roll back to, is it 60601-1 or is it IEC62353? If it's in the manufacturing center in design validation testing, or in the factory in the final assembly testing situation, it is clearly IEC60601-1, and we do all of the tests required under 60601-1. If the device has been delivered to the end user and it is being installed at the end user, from that point on, whether it's by the biomedical department of that facility, whether it's a hospital or other medical facility, or it's the field service engineer for that facility, 62353 is the most appropriate standard to be used. And then we have to decide, is it direct, is it differential, or alternative, and we can follow the manufacturer's advice on that if they give it, or else we can follow the decision trees to see what we need to test. The frequency of testing will be exactly the same as we've already just discussed. Typically, the manufacturer wants it at least once per year, but you follow the manufacturer's inspection procedure is the best advice.
Thank you, Jerry. This is the last question. Is there a book you recommend for following the IEC standards for electrical safety testing?
Well, that's a great question. Everybody should know that Fluke Biomedical publishes in contract with the University of Vermont our medical device equipment quality assurance programs, program development and procedures, but that is a very general category level, medical device category level book. The current editions of that book focus on IEC62353 and really not on anything else. So we're really focused primarily for the end user, hospital, or other medical facility. So there isn't, as far as I know, a widely published, widely available book that clearly defines not only the requirements of the standards, but which one is the right one to use. Now, I know our friends at Rigel have a lot of smaller booklets that they publish, and those are pretty good booklets, I have to say. They're well done. But whether I would lean heavily on that because it's coming from a provider of test equipment, like I wouldn't tell you use something Fluke Biomedical publishes because that's not good enough. I'm sorry, it's not good enough. It's the fox guard in the hen house. We would never advise you to do that. We would tell you to seek more of a textbook or something that would be used in the university that would be able to be more objective. Let me say it that way, more objective and looking at the picture, not from a the point of view that could be questions as to conflict of interest. Okay, we don't want any conflict of interest here. I don't know of a good book that actually covers the subject really, really well. I wish I did. If you find one or if you know of one, I am happy to receive that information on my email, and then I will begin to wrap that into training as advice. But I don't have good advice for you on that one right now. I'm sorry.
Thank you so much, Jerry. We have had so many questions. We will be emailing you to answer them offline. And thank you again to today's sponsors, Fluke Biomedical. One lucky attendee will win lunch for their whole department. Details are included in the post-webinar survey, which will appear on your screen shortly. You must complete the survey to obtain your certificate of attendance. If you do not see the survey, email us at webinar@mdpublishing.com.